Hi everyone, and welcome to our module on hypothesis testing. Hypothesis testing is a critical element of medical research. And what we mean when we say hypothesis testing is we mean determining whether results of scientific studies are meaningful. If a scientific study finds that a drug is beneficial to patients, or it finds that exposure to a certain substance is associated with cancer, we use hypothesis testing to determine whether the observed study findings are real or due to chance. If the findings are real, they could be meaningful to the entire population. Obviously, if they're due to chance, they are not. And so you need to go through this process of hypothesis testing to extrapolate medical testing results to the general population. All medical studies involve a subset of the total population. We're never able to test every single person in the world who might have a certain condition. So we use this process of hypothesis testing, which we'll talk about in this video, to determine whether study findings represent reality in the total population. Usually, hypothesis testing involves comparing two different groups which have different outcomes, and what we're usually asking is, are the differences between groups real, or did they occur due to chance? So to give you a better picture in your mind of what I mean by hypothesis testing, let's talk about an actual clinical trial, and we'll talk about the MERIT heart failure trial, which was a famous cardiology trial that showed that beta blockers lower mortality in patients with systolic heart failure. The study enrolled a little under 4,000 patients, and the patients were randomly assigned to treatment with either metoprolol or placebo. The primary endpoint for the trial was all-cause mortality, and in the placebo group, all-cause mortality was 11%. In the metoprolol group, all-cause mortality was lower at 7.2%. So these findings indicate that metoprolol lowered the risk of dying from heart failure, but we don't know whether that's a real difference or whether it's due to chance, because this trial only involved a little under 4,000 patients, and there are millions of patients in the world with heart failure. So we don't know whether we just happened to select about 4,000 patients in whom this was true, but if we selected a different group it wouldn't be true, or whether this is a real result that would be true no matter which heart failure patients in the world we selected. So the process of hypothesis testing is an attempt to answer the question, is metoprolol truly associated with lower mortality, or was this outcome in the MERIT heart failure trial due to chance? And it's called hypothesis testing because we are testing the hypothesis that metoprolol is associated with lower mortality to try and determine whether that is correct or whether that's not correct and the results of the trial were simply due to chance. So let's come up with our own hypothetical example, and we'll go through the process of hypothesis testing to understand how it's done. Let's imagine there is a protein level called MI-zyme that can be elevated in the plasma in patients with myocardial infarction. And let's imagine we want to measure this level and use it to detect myocardial infarction in patients in the emergency room. So we conduct a clinical trial and we obtain samples of MI-zyme levels in 100 normal subjects who do not have a myocardial infarction, and also 100 subjects who we definitely know have a myocardial infarction based on other testing. And our study finds that the mean level of MI-zyme in normal subjects is 1, and the mean level in patients with myocardial infarction is 10. So these results look promising. The MI-zyme level is much higher in the patients with a myocardial infarction. But remember, we only tested 200 subjects, and we don't know what would happen if we conducted this experiment again on another 200 subjects, or if we use the MI-zyme level in thousands of patients in the real world. So we're going to go through the process of hypothesis testing to try and evaluate whether the MI-zyme level can be used as a test to detect myocardial infarction in the general population outside this group of 200 patients that we studied. So the question we're asking in our example is the mean value of MI-zyme in myocardial infarction subjects truly different from normal subjects, or was the difference we saw in our experiment simply due to chance? And so we're going to test the hypothesis that MI-zyme levels are higher in myocardial infarction patients. So hypothesis testing uses statistics to mathematically calculate probabilities for different outcomes, probabilities like 5% or 50%. So we can use hypothesis testing to determine the probability that the two means from our experiment were truly different. Maybe the probability of that being the case is 50% or 80% or 20%. And we can also determine the probability that the difference is due to chance. The math behind hypothesis testing is complex, and you don't need to know this. It's something statisticians have to learn. But you do need to understand how to interpret the probabilities that come out of hypothesis testing. And in order to understand this, you need to appreciate that those probabilities depend on the data we have. So if we studied 200 patients in our MI-zyme experiment, The probabilities that we get out of hypothesis testing will depend on the difference between the means of normal and MI patients that we find, also the scatter of data and the number of subjects tested. So let's talk about these three things now. So let's imagine that we plotted the MI-zyme level along the x-axis, and each time a patient in our study had a particular value for MI-zyme level, we put a little dot. And we use blue dots like shown here for all the normal patients and red dots for all the MI patients. Well, if the mean value for the normal patients was way over here on the left side of the graph, and the mean value for the MI patients was way over here on the right, then we've got a huge size difference between the two means, and that makes it more likely that these results are real and not due to chance. On the other hand, if we had a situation like on the right side of the screen where the normal patients were here and the MI patients were here, and the means are very close together, that's going to reduce the probability that our finding of different means was real and not due to chance. It's going to be more likely that this was a chance finding because the means are so close together. So the main point here is that the magnitude of the difference in means influences the likelihood that the difference between means is due to chance. As I said, you don't need to know the math behind hypothesis testing, but it takes into account how far apart the means are from one another to determine the probabilities of various outcomes. The scatter of the data is also very important. If all the normal patients are clustered together here around the mean, and all the MI patients are clustered together here around the mean for MI, then we can be more certain that this result is real and not due to chance. On the other hand, if we have a result like on the right side of the screen where the data points are scattered widely and sort of mixing together in the middle here, then this makes it more likely that our finding was due to chance and less likely that it's real. So the scatter of the data points is also important for the likelihood that there's a true difference between means. And then lastly, the number of samples has a big effect on the probabilities from hypothesis testing. If we find means that are separated like shown on the bottom left side of the screen here, but we only have a small number of samples, we can't be so certain that that difference in means is real and not due to chance. On the other hand, if we have lots and lots of samples like on the right, then we can see that the normal patients are truly clustering over here on the left and the MI patients are truly clustering over here on the right, and we can be more confident that these results may be real and not due to chance. So the number of data points also influences the likelihood that there's a true difference between the means. So getting back to our hypothetical experiment, there are two possibilities for the MI-zyme levels in normal patients compared to MI patients. Possibility number one is that MI-zyme does not distinguish between normal and MI patients. In other words, the levels are the same in both groups. Possibility number two is that MI-zyme does distinguish between normal and MI patients and the levels are not the same in both groups. And so really what we've got here are two hypotheses for the relationship between MI-zyme levels in normal patients and MI patients. And we call hypothesis number one the null hypothesis, or H0, and we call hypothesis number two the alternative hypothesis, or H1. Now in reality, either H0 or H1 is correct. And in our experiment, we are going to decide whether or not to select H0 or H1 as correct. And once we've done this, hypothesis testing is going to determine the likelihood that our experiment matches with reality. So there are four possible outcomes for how our experiment matches with reality, and through hypothesis testing, we're going to try and assign a probability to each one. The first possible outcome is that there's a difference between the mean values of MI-zyme level in normal patients and myocardial infarction patients in reality, and that we detected it in our experiment. Essentially, this means that the alternative hypothesis H1 is found true by our study, and it's also true in reality. Second possible outcome is that there's no difference between MI-zyme levels of normal patients and MI patients in reality, and our experiment also finds no difference. This would mean that our experiment finds the null hypothesis to be true, and that is the correct finding based on reality. The third possibility is that there's no difference between MI-zyme levels in reality, but our study finds a difference. This is an error, and this is called a type 1 or alpha error, where our study finds a difference between MI-zyme levels, but it doesn't exist in reality. And then the final possibility is that there's a difference between MI-zyme levels in reality, but our study misses it. This is another type of error called a type 2 or beta error. So we can take these four possible outcomes and put them into a 2x2 table. So in reality, either H1 or H0 is correct. Remember, H1 says that there is a difference between means, and H0 says that there is no difference between means. And then using our experimental data that we collected, we are going to decide whether, based on that data, we think H1 or H0 is correct. And then using hypothesis testing, we can assign a likelihood for each of these four possibilities based on our experimental data, based on the three things we talked about before: the difference between means, the scatter of data, and the number of subjects tested. So if we had a statistician help us and we analyze these things in our data set, we might decide that the likelihood that there is a difference in reality and that our study detected it is 80%. And so that would be the number that would go here. And so if there is a difference in means in reality and there's an 80% chance that we detect it, then there must be a 20% chance that we miss that difference, and that would go here. If in reality there is no difference between means, but we find one in our study, then that percentage would go here, and let's say that would be 5%, and then this number would have to be 95%. And so using the data and analyzing these elements here, we can assign probabilities to four outcomes like shown in this 2x2 table, and this is what's done through hypothesis testing. And so each of those four outcomes has a name in statistics. So if there is a difference in means in reality and our experiment detects it, we call that the power of the study. It's the chance of detecting a difference that exists in reality. If there's no difference in reality, but we find one in our study, that's an error, and we call that an alpha error. That's the chance of seeing a difference that is not real. If there is a difference in means in reality, but we don't detect it in our experiment, that's called a beta error. That's the chance of missing a difference that is really there. And as I told you on the last slide, the power is always equal to 1 minus beta. Remember on the last slide, we said that beta was going to be 20, and therefore power had to be 80. Or if you select a power of 80, then beta has to be 20. So hopefully you're with me so far, and if you are, then we can now talk about the p-value. So if you look at this table on the bottom right side of the screen, I told you that in our experiment, we were going to decide either to accept the alternative hypothesis H1 or the null hypothesis H0. Well, how do we determine which of these two hypotheses to select? And we do this by calculating something called the p-value from our experimental data. This is used to accept or reject a hypothesis. The p-value is calculated through statistics. You don't need to know the math behind it, but it's based on the difference between groups, and it's based on those three elements we talked about earlier: the magnitude of the difference between groups, the scatter of the data, and the number of samples. So the p-value represents the chance that the null hypothesis is correct and that in reality there's no difference between means. And we don't want to reject the null hypothesis unless the p-value is very, very low. And the cutoff that is traditionally used is a p less than 0.05. If the p-value is this low, meaning there's a 5% or less chance that the null hypothesis is correct, then we usually reject the null hypothesis and we say that the difference in means found by the study is statistically significant and likely to represent reality. So looking down at our 2x2 table in the corner of the screen here, using our experimental data, we don't want to reject this null hypothesis unless the chance that it is correct is very, very low, less than 5%. If that's the case, then our experiment will deem H1, the alternative hypothesis, to be correct because the chance that we're wrong is relatively small. And you should be aware that the p-value represents the chance of a false positive finding in a clinical study. A false positive finding occurs when there's no difference in reality, but the study finds a difference that is not real and simply due to chance. And because the p-value represents the chance of a false positive finding, it has to be very low, less than 0.05, for us to consider the findings of a clinical study to be positive. If the p-value is above 0.05, the likelihood that the findings are due simply to chance and are not real is too high, and therefore we consider the study to have a negative finding. And you should be aware that the p-value is similar to but different from the alpha, which is also called the significance level. In our 2x2 table, we talked earlier about how this is the alpha value here. It's the chance that there's no difference in reality, but we detect one in our study, which is another way of saying a false positive. The difference between the p-value and alpha is that the alpha level is set by study design, and the p-value is calculated by a comparison of the two groups. And usually studies are designed to have a likelihood of an alpha error equal to 0.05 or less, so that the study will be able to generate a p-value equal to 0.05 or less. So let's go back to our example of the MERIT heart failure trial with about 4,000 patients with systolic heart failure. In the placebo group, the all-cause mortality was 11%, and in the metoprolol group, the all-cause mortality was 7.2%. The p-value for this difference calculated based on the data from the patients was 0.00009. So as you can see, that's much less than 0.05. So the study authors rejected the null hypothesis that this difference in outcomes was due to chance, and they accepted the alternative hypothesis that metoprolol reduces mortality. And this is referred to as a positive study that finds a positive benefit of a drug. Now let me talk in a little bit more detail about the power of a study, which, as I told you before, is the chance of finding a difference when one exists. If we look at our 2x2 table, this is the power. There is a difference in reality, and we identify a difference in our experiment. This is also called rejecting the null hypothesis, because when we identify a difference in our study, we necessarily reject the null hypothesis. And the power of a study is increased when you have a larger sample size, a large difference between the means, or less scatter of data, all those things I talked about earlier in this video. And I've bolded increased sample size because when you're conducting a study, the one thing you have control over is the sample size. You can choose to study fewer or more patients, and that allows you to manipulate the power. So when researchers are conducting studies, they do what's known as a power calculation, and the idea is they want to maximize the power of their study to detect a true difference. You don't want to waste a lot of time on a study if there's only a 5% chance you're going to be able to identify a difference that exists. You want the chance to be much higher than that, so conducting the study is worth your time. Now, when you're designing a study, you usually have very little or no control over the scatter of the data or the difference between means. These things have to do with nature and the way phenomena occur in nature, and they're going to be what they're going to be. But you do have control over the number of subjects. You can choose to study more or less subjects to generate the power that you want for your study. So before researchers conduct a study, they always do a power calculation, and they identify the number of subjects they will need to have a high power of the study. Usually the goal for power is 80%, and determining the number of subjects needed to have a power of 80% to detect a difference that exists in reality is called a power calculation. Let me make a brief comment on some of the terminology that's used around statistics in clinical studies. You will often hear the term detecting a difference, and let's talk about what that means. So imagine we had a study that found an outcome of 10% in group A and 20% in group B, and the p-value for the comparison of the different outcomes was 0.001, which is less than 0.05, so it's statistically significant. You will often hear it said that this study detected a difference, and what they mean is that the difference between the two groups was found to be statistically significant with a p-value less than 0.05. Now let's imagine another study finds an outcome of 10% in group A and 20% in group B, but the p-value is 0.25, which is not statistically significant because it's greater than 0.05. For this study, we will say the study did not detect a difference. Now obviously there is a difference between groups, but the difference was not statistically significant. So we say the study did not detect a difference. And this outcome here, where you have a difference between groups, but it's not statistically significant, is heavily influenced by the power of your study. If you don't have enough patients and the power is low, you will often get the outcome of study 2. On the other hand, if you have lots and lots of patients, you're more likely to get the outcome in study 1, where you do detect a statistically significant difference. I'll finish this video by talking about statistical errors, and we'll start by talking about a type 1 or alpha error, which, as I told you before, is a false positive. This type of error occurs when our experiment finds a difference or an effect, but there is none in reality. Statisticians think of this as rejecting the null hypothesis when you should not have. And so an example of a type 1 error might be where researchers conclude a drug benefits patients, but later evidence emerges and it turns out that it did not. That's called an alpha error. In reality, there was no difference, but we found a difference in our study. So what are some of the causes of type 1 errors where, for example, researchers conclude a drug benefits a patient, but it does not? One of the main reasons these type of errors occur is random chance. In most studies, we set the chance of an alpha error at 5%. This means that 1 out of 20 times we're going to have an error in our findings. As I told you before, studies are considered positive if the p-value is less than 0.05, but this doesn't mean there's no chance that the study findings are wrong. It just means that the chance is less than 5%. So if you conduct enough research studies, from time to time one of them is going to have an erroneous finding. And that's why before we put things into practice in medicine, we like to have multiple studies showing it works, so that we know we're not just relying on a single study which could be an error. And then another reason you can get a type 1 error is if there are improper research techniques and the outcomes aren't assessed properly. This is uncommon when medical research is done formally at institutions that have rigid standards. A type 2 error is a beta error. This is a false negative. This means we find no difference or effect, but there is one in reality. Statisticians think of this as accepting the null hypothesis when we should not have. Once again, looking at our table, this is a beta error here, so there's a difference in reality, but our study doesn't detect it. So an example of this type of error could be researchers conclude that a drug does not benefit patients because the study has a high p-value, but then subsequent studies find that the drug actually does work. That's a type 2 or beta error. Far and away, the most common cause for this type of error is too few patients. Remember what I told you before, you need lots of patients to have sufficient power for a study. This is especially true when the differences in outcomes between groups are small. If two groups have outcomes that are very close together, you're going to need lots of patients to prove that that small difference is true in reality and not due to chance. Another way you can think about this is a significant p-value less than 0.05 is more likely when there's a large difference between groups or a large number of patients. Now, as I said before, you usually can't control the difference between groups. That's going to be whatever it's going to be based on nature and naturally occurring phenomena. But you do have control over the number of patients. And so if you don't enroll a large number of patients in your study, you will often have a type 2 or beta error. And this is a big problem when medical students do research projects. There's not enough time to recruit 10,000 patients, so you recruit 20. And often you find that there's no difference between groups. That could be a beta error, and if you had time and ability to recruit 10,000 patients, you might find a difference, but you're not going to find a difference with only 10 patients. It's simply too few patients. And that concludes our module on hypothesis testing.